chose this topic because, at the end, I'm going to make a few comments on importance of working with industry and trying to solve real world problems. So before I get started, I want to acknowledge a few people here. My former graduate research assistant, Richard Seichek, he did his master's thesis on this many years ago. He currently is environmental engineer with U.S. Army Corps of Engineers. Rich did his bachelor's, master's, PhD at UIC. Of course, his PhD topic was on electrokinetics. It was different than master's topic. So I'm happy to see him join this webinar. I asked him to join because I'm presenting his work from his MS thesis. So it would be nice for him to recall what he has done. And I want to thank my collaborators. At that time, these companies have changed their names, but Trust Environment Infrastructure, Sanjeev Bundy, he may be online, and Mike Britton, John Rohr, Jim Walker. These are the guys, who kind of, highlighted the importance of doing research on this topic and collaborated with me to do this one. And Waste Management, Mo Finney, he's also supposed to join the call. Hopefully he did. And he's the site engineer at Landfill, where we did all the work. So, and National Seal Company, John Sibkin, and then Ohio Environmental Protection Agency, they were instrumental in having this kind of research done. The funding was provided by Waste Management and the University of Illinois at Chicago. So in my presentation, what I'm going to do is give you a brief introduction to landfill liner systems. Many of you are already familiar with these things, but I just want to give a high-level overview of what we are really focusing on. Within these liner systems, we use the geomembrane. What is the need for geomembrane protection? And then I'm going to talk about our project goals. Our project goals was to, protect the geomembrane liner from, leachate drainage layer that could consist of granular soil, or, these days people are thinking about using, waste materials such as tire shreds or glass cullet. So, and in all these cases, we need to protect the geomembrane, and if there is going to be any damage, can we use a geotextile cushion to prevent that damage? So that's kind of our project goal. And for achieving these project goals, we had to do a lot of field testing and test pads to simulate construction loading and damage to the geomembrane during the construction. And then we had to do some lab testing to simulate the long-term municipal solid waste loading. And in these construction loading conditions and long-term municipal solid waste loading conditions, how would the geomembrane be protected? And we drew some recommendations, and then I will make some closing comments. So that's the agenda for today's presentation. Now, taking you at a high level, municipal solid waste landfill liners and cover systems. So many of you are already know this. There is a bottom liner system and side liner system, and then you fill it up with the waste and you put a final cover system. And the liner system consists of a composite liner, and you have a leachate collection and removal system. And then zooming in on we cover these design of landfill liners and cover systems in short courses and in university level courses. For example, I use this book to teach landfill design at my university. In this book, there's chapters 15 to 22 deal with this design of landfill liners and covers, as well as other topics related to landfills. So now let's focus on the bottom liner. If you look at the bottom liner, per regulatory requirements, you need to have a composite liner. So basically, you have a compacted clay liner, And then on the top of it, you have a geomembrane liner. So that's the minimum that is required as per US EPA subtitle D regulations. So the minimum thickness of this compacted soil layer is 2 feet. And the other requirement is that permeability has to be less than 10 to the power of minus 7 centimeter per second. So that's the requirement on a compacted soil or compacted clay. And then on the top of it, you need to have a flexible membrane liner. And generally, it is recommended to be 60 mil HDPE geomembrane. 60 mil is very thin. That's a 1.5 millimeters thickness. Plastic sheet that goes on the top of the clay layer. So all the landfills, municipal solid waste landfills have to have this composite liner system implemented. So just wanted you to see what is geomembrane. This whole topic is on geomembrane, and I wanted to just put this picture to show you what a geomembrane looks like. It comes in rolls to the site, and then you spread them out, and then you weld them. And it's as I mentioned, it's a very thin geomembrane, and it's a very delicate. So you really have to install very carefully. If you are careless, if you punctured, made holes and damaged during the construction, it's as good as not placing it. So it's very, very important to install this one, and also after installing and protecting it from any kind of damage is very important, because that composite liner works well only when you have this geomembrane along with the compacted clay, working together as a composite liner. So if it is not, um, you know, um, uh, intact, then you're going to, you're not serving the purpose. So, then on the top of the liner system, you need to have a leachate collection and removal system. And waste degrades, or there may be infiltration of the precipitation, rainfall, all that becomes a leachate, and it comes into the bottom of the landfill. And the regulations say that you need to have this leachate collection system. Such that leachate head on the top of the liner never exceeds one foot. Okay, that's 0.3 meters. So the regulations don't say what you need to do in these things. I'm showing a drainage layer and then showing drainage pipes, and that's how generally this requirement is achieved. So you cannot have a leachate accumulated on the top of the liner more than 1 foot anytime during the life of the landfill. And so that, kind of makes you think, what should I do to achieve that one? So the regulations don't say about using the, drainage layer, using the pipes, but they want you to demonstrate that you can actually, have that 1 foot, not exceed the 1 foot leachate head. Federal regulations don't have any requirements, but some state regulations might have some requirements. Generally, you don't, need to exceed, you should not exceed more than 1 foot. So there's no point in having more than 1 foot of the drainage layer. So generally they put like 1 foot of drainage layer. And sometimes they have a requirement that, permeability has to be greater than 10 to the power of minus 3 centimeter per second. Sometimes they have a 10 to the power of minus 2 centimeter per second. So you really have to look at which state you are working and what are the applicable regulations in that one. And most of the times that drainage layer is a sand. And So this is what goes on. Basically, you have a 1 foot of sand and with a network of piping that basically, whatever the leachate comes in, that gets removed and you will never have accumulation of leachate head on the top of the liner. So protection of the geomembrane is extremely important at all times. So one of the things that you should think about is that geomembrane is there. On the top of it, you're going to have a drainage layer, and you need to select that drainage layer material, such that it does not damage the geomembrane. Most of the time sand is used as a drainage material. So, sand does not, cause any damage to the geomembrane. But if you think about, instead of sand, if I use a gravel layer, it could be crushed gravel, it could have sharp edges, when you put it on the top of the geomembrane, it might puncture and make a hole, right? So, or, in the worst case, you think about tire shreds that have steel in it, and if you put directly on the top of the geomembrane, and the geomembrane could be punctured, could have a problem, some scratches, some kind of problems to the geomembrane. So if you just look at in terms of the meeting the regulatory requirements, that meeting the leachate head of 1 foot is easily possible with any of these materials, because these materials are highly permeable materials. So, in terms of the drainage purposes, these are very good. But only question is, okay, they are permeable, but if I use directly on the top of the geomembrane, what is the potential for damaging the geomembrane? As I mentioned, geomembrane is a very thin plastic sheet, and you don't want to cause any tear or puncture or any major damage to the geomembrane. Because remember, the whole containment efficiency really depends upon the integrity of the geomembrane. So question is, if I want to use, these materials, rather than sand, if I want to use gravel or tire shreds, how can I want to use them, but I don't want to damage the geomembrane. So what are the options that I have? So in that case, you need to put a geotextile, separating the geomembrane and the drainage layer. But the regulations do not stipulate any requirements on geomembrane protection. If you look at subtitle D, there is nothing mentioned about the geomembrane protection. So as I said, sand is commonly used as a drainage material. So the geomembrane protection is not a concern. But questions arise when you use gravel. When you say gravel, it could be very coarse grain, large size particles, to the fine gravel. They have a small size gravel particles. And in terms of their shape, they could be angular, subangular, rounded. The shape of those particles could be different. And if you're thinking about waste and recycled materials, think about tire shreds, glass cullets. They are excellent, in terms of drainage, right? And they have high permeability. So those will be excellent materials to use as a drainage material. But you could have a damage to the geomembrane. Geosynthetics such as geocomposites are used for drainage purposes, but they're not used in the bottom liners. They could be used on the side liner, they could be used in the cover system, but not in the bottom liner, because you have to take out the leachate from the bottom. So sometimes you want to use this gravel or waste materials because they are locally available, right? So if they are locally available, if sand is only available at a site which is very far away, then you have to transport it and all those things, public safety issues, emissions issues. And bottom line for most of the landfill owners is the cost, right? If you have a locally available material at low cost, you want to use that material instead of getting a material at high cost from a further distance. And of course, waste and recycled materials are also important from reuse of waste materials, reducing the waste generation and conserving the natural resources. So you want to use these materials. So when you want to use these materials, protecting the geomembrane comes into picture, but US regulations do not stipulate any requirements on this one. But if you look at if any other countries have any regulations on this protection of geomembrane, Germany has some requirements on protecting the geomembrane. They actually require a separate layer on the top of the geomembrane as a protective cover layer. They call it protective cover layer. And then on the top of that, your drainage layer is constructed. So if I show you schematically, here is your clay liner constructed in layers, and then you have a geomembrane liner, and then on the top of the geomembrane liner, you see the protective cover. So this is a new layer that you haven't seen before. And then on the top of that, you have a drainage layer and the pipes that goes in there. And German researchers have done a lot of studies to look at what are the different types of protective cover layers are possible. So people have done research, and so they proposed all these kind of materials as to use in the protective cover. And they also have a selection criteria. What is the criteria? So whatever, the protective cover that you want to use, that should not induce strain more than 0.25% in the geomembrane. So that's the kind of a criteria that they have for selection of this protective cover layer. Now, common, even though many are suggested, but the common ones are non-woven geotextile with the mass per unit area greater than 2,000 grams per square meter. So this is a heavy, very thick geotextile they recommend. Or they recommend, sand-filled geotextiles or woven mattresses, or a non-woven geotextile, with mass per unit area greater than 1,200 grams per square meters. And then on the top of it, they want you to put a layer of coarse soil with the thickness 15 centimeters or greater. So as you see that's they are specifying a new layer on the top of the geomembrane, specifically to protect the geomembrane. And more than that, in Germany, they use even a thicker geomembrane. So in US, we use 1.5 millimeter thickness geomembrane, but in Germany, they want you to use even thicker membrane. And also, they require drainage media to be a coarse gravel, 16 to 32 millimeter gradation. That is important because, of clogging issues, those things are become important in the long run. So if you look at all these things, this is, very conservative design, right? So you need to have a thicker geomembrane. You need to have a, very, good protective layer on the top of the geomembrane. And then you have, drainage layer like what everyone else does it. Do you need this much, conservative design? Do you need this kind of conservative design? So that's kind of the focus of our research is to, look at something that is rational, not just make it, overly conservative. So how do we do that one? So our project goals were, can we make a drainage media layer, itself to function as a geomembrane protection layer, as well as drainage layer. So as I said, sand is okay, it can do both functions, But when I use gravel and tire sheds, what will I do to protect the geomembrane? So that's the question that we want to answer. If not, the easiest thing that we can do in terms of the protection is to place a geotextile on the top of the geomembrane. Uh, the geotextile is the protection that's kind of easy to put it on. Then do we need it? And if we need it, what type of a geotextile that we need it? So our overall goal is to protect the geomembrane, right, from puncturing, tearing, and so forth. And also, we want to make sure that this happens during the construction, as well as when the waste is placed and in the long run, right? So you want to make sure that geomembrane is protected during the construction as well as in the long run, after placing the waste. So to achieve those project goals, we had to do certain tasks. And so this is our project scope. So first we had to kind of identify what are the different granular soils that could be used as drainage media. And also in this investigation, we looked at tire sheds as a potential drainage media. And then we wanted to conduct, field tests to simulate the construction conditions and see, if geomembrane undergoes any damage, and if we can use the geotextile to avoid the damage. So that is only during the construction. What happens, when you place the waste, in the long run, long-term conditions? So that you cannot do much in the field. We had to do in the lab. We had to create a big tank and then simulate the liner and the waste loading and look at that geomembrane under long-term conditions. So at the end of this testing, we wanted to give recommendations on drainage media, of course, other than sand, we're talking about gravel or tire sheds, and what kind of a geotextile cushion that we need to provide so that geomembrane is protected. So during our first stage of this project, we identified a lot of different soils. Of course, the sand is the common one that is used, but when you talk about gravel, you could have a very fine gravel, medium gravel, crushed gravel. So we found out what are the typical gravel, that can be available, that can be used. So we did the grain size distribution analysis, which tried to characterize these soils. So these are the common types of granular soils that are potentially used as a drainage material. And the first and foremost criteria for serving as a drainage layer is meeting the permeability requirements. Remember, as I said, 10 to the power of -3 or -2, it could be the state requirement, but there's no federal requirement on the permeability. Then, if you look at this D50 average size, we kind of we got these different sizes represented here, sand, gravel, so 0.65 to 30 millimeter average size particles included in that. And then when you're talking about the geomembrane protection, not only the size but also the shape of the particles becomes important. So these are mostly rounded or sub-rounded and subangular. And then we could, calculate the sphericity with using these standard methods. So that could give us some idea. But, we don't see, if you go back to this one, we don't see too much distinction in terms of the particle shapes. We really wanted to see something very distinct in this sphericity, but the soils that we used, they didn't have that much variation. And when you are doing the testing, especially these high permeable soils, you need to worry about having a big constant head permeameter, because you cannot use the small one that you typically use in soil slabs. So you should think about having a permeameter with more flow capacity than the flow that you expect under high permeability material conditions. As I said, the other materials that we wanted to test is waste materials. The tire shreds are commonly available. You need to shed them before you dispose. And if you use, if you run the tires through the shredder once, you basically get the primary shred, like what I'm showing here, right? So it's running through the shredder once. But if you run through a couple of times through the shredder, so you get the tires shreds look like this, small pieces like this. So obviously you want to use the primary, or you want to use the secondary. So in our research, we try to look at which one is more convenient to use, or and this is good because you're converting waste into resource, and conserving the natural resources and the low cost. But we don't want to compromise the technical performance of it. So that's the reason why we need to do this research and see if these materials can perform as good as our granular soils. Remember that both tires have tire shreds have exposed steel. That is really immediate concern in terms of the geomembrane protection, right? So if you are putting this one directly on the top of the geomembrane, all that steel, exposed steel, will puncture through the geomembrane and damage the geomembrane. So definitely you need a geotextile cushion, but what kind of a geotextile cushion you need? Also, these tire shreds get compressed quite a bit, right? They're very compressible. Even after getting compressed, they will have high permeability, but what should be the thickness that you need to use it so that you can maintain certain thickness even after compression. So this is the grain size, the particle size distribution, tire shred size distribution. So obviously the primary one has the big pieces, and there's secondary one has smaller sizes. Again, you need to think about, hydraulic conductivity is the first requirement. And for determining the hydraulic conductivity, then you need to have this large scale permeameter so that you can, measure the permeability. And also, for tires, it is very important to measure the permeability under, different loading conditions, because they are compressible and permeability reduces significantly. So we use a setup like this one to measure the permeability. And testing the secondary tires, you can see compressibility could be as high as 60%, depending upon the applied stress. And sorry, compressibility, and then permeability, in the beginning, it's kind of even the permeameter that we had, could not even measure it. The permeability was much more than the outflow capacity of the permeameter. It's very, very high. And then, as you compress it, the permeability goes down. But even after having close to 1,000 kPa, the hydraulic conductivity is higher than the required value of 10 to the power of -2 or -3. So which is good, right? So we characterized that one, and then we went to the field to assess the damage to the geomembrane during the construction. So the question here is, a lot of times you construct the compacted clay liner first, and then you place the geomembrane, and then you place the drainage material, and you use the construction equipment. So it will be very critical, like, you don't have a lot of distance from the construction loading to the geomembrane. And what is the chances of, having high concentrated stresses right at the interface between the drainage particles and the geomembrane? And as a result of that, there could be damage to the geomembrane. It could be puncturing, or you could be making, dents and other things, so that you're basically weakening the geomembrane. So during the construction, you could be causing a lot of these high concentrated stresses. And to look at that one, we created this field testing program. We tested these three materials: medium gravel, fine gravel, and light shreds, and with and without geotextile cushion. And then we used, two different types of construction equipment, the light dozer and heavy dozer. So obviously heavy dozer means, you have a heavy load that's coming on it, high stress is being applied. Light dozer means less stress that is applied on that, right? So, and this is the best way to see what happens to the geomembrane. You could do a lot of things in the lab, but that never represents the reality, right? So doing this field testing is extremely important. So so Mo Finney, was the collaborator from waste management company, and this is the landfill where we were doing this field test. This is the landfill site in Ohio. So we found a level ground, and then we compacted the soil to represent the typical compacted clay liner, and then we checked it for any rock or anything protruding from this the clay liner, right? You just the clay basically here. The soil here is a silty clay that's commonly used as a drainage material, as a liner material. And just after compacting, and we just checked for any protrusions that might be damaging the geomembrane. So that one. And then this here is a geomembrane. You place it at one end and then unroll it. Um, this 1.5 millimeter thick smooth HDPE geomembrane that is commonly used as in the composite liner system. Um, and then yeah, then we visually, you look at the geomembrane, see if there are any, damage that might have happened during the transportation and storage. So, um, and then if we needed, in some testing cases, we use the geotextile cushion on the top of the geomembrane. So if we are doing that kind of testing, that kind of conditions for testing, then we would put a geotextile on the top of it. And then this is how it will look, kind of a test pad. And So you have a compacted clay in the bottom and geomembrane on the top of it. And then sometimes we don't have any geotextile in some cases. In some cases we have geotextile. I'm just showing you, as a geotextile here, with a geotextile here. Then we put the stakes all around, and we mark with a ribbon how high the material to be placed on this. So on the top of this one, you're going to put a drainage material, right? So 0.3 meters, that 1 foot is this. So the construction guys know how the thickness, what should be the thicknesses. So, we try to simulate the typical construction of liner and placement of this drainage material, how it is done on a full-scale landfill construction, right? So generally, we bring the drainage material and dump it at one end. That's what is shown here. And then you try to spread it onto the liner system, as you see here, right? And you will not let this construction equipment go onto the geomembrane liner unless you have a minimum thickness of the drainage layer. So you just keep putting more drainage material. And once you have enough material, as you put more material, as soon as you have enough thickness, then you can have your equipment go on it. So in this case, we placed all the, material, as you see here, is one of the gravels that we tested. And then, after placing the drainage material, we had this dozer, go forward and backward multiple times. And we had it turn it and then, reverse it and then apply the brakes. So we kind of, made this equipment, to simulate, the worst case construction scenarios where, there's a lot of movement of this kind of equipment going back and forth, maybe applying the brakes, turning, and all those things. So we kind of, created all those things on top of each of these test pads. So here are the people watching. I wanted to show this one because these are all from Ohio Environmental Protection Agency, and they were expressing the concern that the use of gravel could damage the geomembrane. And this project is undertaken, to show them that you could use gravel as a drainage material, but you need to provide geotextile cushion. So they were there, to watch this whole thing. It's very important, to work academics, industry people, and regulating agencies together and to come up with a solution to the problems that we're facing. So that's the point here. I think this is Mo Finney here, and Sanjeev Bundy is here, and I'm there somewhere. Rich is also there somewhere. So we did, some test pads with this heavy dozer D7. D7 has, the contact pressure of 46 kPa. And then we also wanted to test, the lightweight, dozer. So this dozer D4 that has a pressure of 29 kPa. So we wanted to redo the same kind of testing with a light dozer. Again, we had these test pads, and then test the material at one end, and then put it on, push it on to the liner. And then, you advance the equipment, by maintaining certain height of the drainage material, so that you're not directly or you're not excessively stressing the geomembrane at the bottom. So all the construction equipment loading is applied, on the top of this drainage material, which is 1 foot thickness. So same thing, you spread the whole thing, so here shows the test pads, and again, this going back and forth, turning, all these maneuvers are done. So, this created the worst case scenarios. So if there is a damage to the geomembrane, you would definitely, created a worst case conditions to see that kind of damage. So this all. So once we have done that one, so we want to know, what happens to the geomembrane, right? So what is the extent of damage to the geomembrane? So how do we do that one? So only way is to exhume the geomembrane and see it, right? So we had this, backhoe, and we want to be very careful, in removing the gravel and to exhume the geomembrane, because you don't want to cause the damage, by following a careless process. So we have this backhoe with a rubber-lined bucket edge, and then just the top, few inches of the drainage material was taken out, and after that we use the shovels to remove the gravel, so that the geomembrane is not affected. And then we use the rag and cleaned it, and then we cut the geomembrane, and we chose the locations where we we thought, the geomembrane was excessively stressed during these construction operations. And as you see, all these regulating agencies are watching. Everyone is anxious about looking at what happened to the geomembrane, uh, under these conditions. So this is Sanjeev Bundy, is helping out, cutting that one. This is me, and I think Mo is somewhere here. And so here, everybody is watching. So you can see, very keen interest on looking at what happened to the geomembrane. So if we had a geotextile, we take out the geotextile from the top, cut it out, and then we retrieve the geomembrane sample. So here is the geomembrane after testing. So then, we need to do the assessment of the damage to the geomembrane. So obviously we can do the visual observations, see if anything is damaged, but that's not enough, right? I mean, you could probably see some scratches and all those things. What does that mean? Just a simple superficial scratches mean, the geomembrane is damaged, it's not going to look like, getting out of, manufacturing plant, you are putting the soil on top of it. So there will be some light scratches, but we wanted to test that material. Obviously, if there is a damage, if there is a hole or dent in that, that it's damaged, so you don't have to do any kind of testing. But if you have just a little bit of scratches, but you don't know if it is damaged or not, so we try to do this test, water vapor transmission test, to look at if there is any change in the permeability of the geomembrane. So we did some multi-axial tension tests, wide strip tensile tests to look at any kind of physical damage to the geomembranes. And then we compared with virgin geomembrane samples. So we also tested the virgin geomembrane sample that is straight from from the roll that is not used in the test pads. So basically, we wanted to compare how the results of these exhumed geomembranes compare with the virgin geomembrane samples. So visual observations, the many eyes looking at the exhumed geomembranes and trying to find out where dents are, where scratches are, so we looked at all these things again, multiple times in the field and multiple times in the lab. I know Rich spent a lot of time looking at these things. Even he used the magnifying glasses to look at where the damage is. So we have visual observations. And then we did this water vapor transmission test on the samples that we got. So, water vapor transmission tests are done according to ASTM E96. So basically you cut a sample of that geomembrane, the exhumed geomembrane, and put it in these, discs, put water inside, and then put it in them under controlled temperature and humidity. And you weigh, the weight loss, and because, the permeability of the geomembrane is so low, you cannot do the traditional permeability test, right? You cannot, so this is the indirect way to know, the permeability of the geomembrane. So, from each geomembrane, there were like 3 samples were tested. And then here are the results. So what I'm showing is these are the test conditions: 1, 2, 3, 4, 5, 6, 7. These are 7 different test plots. And these are the geomembrane samples that are exhumed from there. And what I'm showing here is the average permeance. It's almost like a permeability, right? So I'm showing here virgin 1.5 millimeter HDPE geomembrane, the average of 3 samples, how much it is. So this dashed line shows the virgin sample. And here are the exhumed samples. So here you can see the medium gravel, medium gravel, and then the last 4 are with the fine gravel. And here is the combinations. You don't have a geotextile, there's no geotextile, and light doser, a heavy doser, and with a geotextile, light doser. So you can see, without geotextile, with geotextile, light doser, and heavy doser. So these are the variables. So variables are, this soil type, and whether we use the geotextile or not, whether we use the light doser or heavy doser. And you can see that, these values are 10 to the power minus 15 centimeter per second per Pascal. Even though you see some like a difference, but that difference is, within the experimental error. So because, weigh the samples, and during the entire test duration, the mass loss was only 4 milligrams. So it's a very minor weight loss. Any small errors in that, those weights will show that small difference. But irrespective of, those variations, small variations you see it, the average permeance of exhumed samples, all of them, is still, 10 to the power minus 15, and virgin sample also 10 to the power minus 15. So practically there is no difference between exhumed samples and the virgin samples. So this implies that the permeability of the geomembrane did not change due to different granular soils or geotextile cushion combinations that are tested in this study. So this is very good news. So all the things we did, it's good. But that test, water vapor transmission test, gives only the permeability. It does not indicate the physical damage that could have occurred in the geomembranes. So this multi-axial tension test is done. This is done according to the ASTM D5617. So basically, you take a bigger sample. You have a 0.6 millimeter diameter sample. You clamp it, and you pressurize from inside. So and then it bursts, right, after a certain pressure. So this is the 0.6 meter is kind of a standard. You could also do it in the 0.3 meter diameter sample. We did some samples on both size samples, and we found that the results are pretty similar. So you could use either one. But obviously, the larger the sample, better it is, because especially the exhumed samples, they could have non-uniform damage, and then using the bigger sample would capture as many those damage features as possible. So basically, when you put the sample here and pressurize it, if that geomembrane has undergone some damage, that will be reflected in the stress that is required to burst it, right? And how much is the strain that is required in that one. So that will show it. So here are the results for the same 7 test pads, the geomembranes. Again, all of these, I should have shown error bars, but on each test pad, we had 3 samples tested. This is the average values of those, the 3 tests that are done on each geomembrane. So here is the virgin HTP geomembrane. I'm showing it's the tensile stress at burst. How much is the maximum stress that you apply so that sample get bursted at the end, right? And you can see that exhumed samples had exactly same, almost the same average tensile stress as the virgin sample. So this shows that there's not much physical damages happen. On the other hand, if you look at from the same test, you get the elongation it bursts. How much it has to expand before it bursts, right? That varied. It's with that kind of a very nice to see that, at least for us. If this was also equal, then we don't have any way to say any damages occurred. But this showed like a different values. So, this would have gone about 25% virgin sample. But these, the exhumed samples, look at that, they without geomembrane, light or heavy, they failed at a lower elongation. You can see here. But when you have a geotextile, right? Yeah, in these 3 cases, you can see these geotextiles, and you had same or even slightly higher elongation at burst. So indirectly these will reflect the physical changes that could have happened in the geomembrane in the test pads. So when you use the geotextile, as light as 270 grams per meter squared, not like very thick one that the German regulations require, we can, get the properties similar to the virgin sample. So that's kind of a lesson learned here. Yeah, there are some physical damages that have happened to the geomembranes that are reflected in this, elongation at burst. But when you use the geotextile, then, that damage is not existing. Then the failure modes, we found out that, the failure modes could be different, but rupture initiated near the top of the dome for all the samples. So that was one of the things that we were observing it, if there were, damages that have happened at other locations, maybe that's where, the rupture initiates. That was not true because, the, there were no, significant damages across, at other locations to initiate that kind of rupture. So in all these cases, rupture started at the dome, and then, but depending upon the physical damages, the failure mode varied in the sample. So the, identifying where rupture started, could not give us any. There were no differences, so that could not give us any indication on, clear damage points on the geomembranes. Then we did wide strip tensile test. So basically, these are the kind of standard tests that are done on geomembranes, ASTM D4885. You can take a sample, you clamp it, and then you apply tension. And they can, elongate so much. I'm showing you an example of this. Um, and in some cases you have elongation. In some cases, if damaged, then you could see that reflected in the how much is the the strain that you have for yield or for break, right? So for all the samples, we did the testing on this, and you look at these results here for 7 conditions. So the stress at yield, right? Just the yield, there's not much difference. So they're all like same as virgin samples. So until yield, nothing is changed. The strain at yield also did not change that much, right? But secant modulus also kind of the same thing based on that. But stress at break, where this whole thing as samples have broken, that captures even those minute physical damages that have happened in the geomembrane. So that can be seen in these results, right? So average stress at break you can see, but the ones with the geotextile, did not, the difference with the virgin was comparatively less compared to the other ones. So again, this is the percentage strain at break also varied. And remember, I showed you, the sample one breaking early, other one stretching so much. So, some of the physical damages that have happened, could be responsible for samples breaking up at less strain compared to the samples that are protected with the geotextile. So, obviously, based on these results, you can clearly, make one conclusion or recommendation that, hey, if I'm using, this, gravelly soils, whether it's a medium gravel or fine gravel, if I'm using, heavy dozer or light dozer, the conclusion is, we can use, even a lighter, geotextile would be sufficient to protect the geomembrane. So same thing with load versus load width ratio. So the findings from this one is that none of the geomembranes had apparent visual damage in the geomembranes, and water vapor transmission tests showed that permeability do not change much, so which is good. And the stress at burst determined from multi-axial tests, and the yield stress and strain determined from the wide distributed tensile stress did not change, so they did not indicate the damage, but elongation at burst and then ultimate or break stress and strain from multi-axial, the wide strip tensile test, they indicated the physical damage. So, although the physical damage, has happened, but the geotextile seem to protect the geomembrane quite nicely. And we don't need to look into like a very thick geotextile, but as light as 270 grams per meter square geotextile would be good enough to protect. So then after the field test, we wanted to do a lab test to simulate what happens to the long-term conditions. So you constructed it, you construct the drainage layer, and after that you start placing the waste, right? And then as you place the waste, you are increasing the stresses on the drainage layer, and then those stresses are transferred to the geomembrane, right? So what happens to that? So that's what I'm showing you here. You have a compacted clay, geomembrane, and you could have a geotextile cushion, and then you could have the drainage layer, and then you're piling up the materials. In some cases, you could have 100 meters of waste, so it's 300 feet of the waste on top of the drainage layer. So how do you address that one? So you're applying so much stress, and what happens to the geomembrane liner? So for testing that one, we did this in the lab. So we had this simulation testing apparatus. So we had this big test box created with inside dimensions I'm showing here. And what we have here is at the bottom, we have the elastomer pad to represent the compacted clay, and then we have a geomembrane on the top of it. And then optionally, we may have used the geotextile. In some tests, we didn't use the geotextile on the top of it. And then we placed the drainage material on the top of it. And then we put a loading plate on top of it. And then we apply the load. So we applied the load, in increments. And we take up to 1.4 megapascal. In this case, we wanted to simulate 100 meters of waste. And then we leave it for 48 hours. And then we carefully release the stress, take out the plate, take out the soil, and take out the geotextile if you used it, and then retrieve the geomembrane and look at how much damage it has gone through it. Elastomer, because it's in this test, compacting the real clay is difficult, and we wanted to simulate exactly the same conditions in every test. So we did some consolidation tests with clay, and then we did tests with the different elastomers. So, we picked the elastomer that gives the same kind of compressibility as the compacted clay. That way, we could mimic exactly the same compacted clay conditions in all these tests. So we did these tests, look at this, crushed gravel with geotextile, without geotextile, medium gravel, fine gravel, very fine gravel, medium sand, with and without geotextile. So the whole idea is to look at, these materials, how they perform under, long-term stress conditions, right? So we varied the soil type is main thing, and the geotextile. Again, we wanted to use the light geotextile, and see how it performs. And then we took out the samples, and then visually we observed it. And this is all done by my student Rich Saichek for his master's thesis. There was visual damage in the form of dents and creases when we used the crushed gravel, medium gravel, and fine gravel. And when you use the geotextile, the visual damage was less. Very fine gravel had very small dents, but when we use the geotextile, those were also reduced. The medium sand visually didn't have any damages with or without geotextile. So this is what we kind of expected it. That's fine, but how do we quantify the damage, right? And we also analyzed the granular material that we took it out after loading, see if the particles crushed, gradation has changed or not. So we did that grain size distribution after retrieving this, after testing. So we didn't find any gradation changes. So the soil does not undergo any changes. So here are the results for those 5 different materials that we are testing, with geotextile, without geotextile. The first one is without geotextile, and the second one is with geotextile. And I'm looking at the same kind of test that we did for the field test. We are doing it here also, water vapor transmission test, right? So this is the virgin sample results. And then, you can look at it when we have a geotextile protection. We had, and also this, as I pointed out, this minus 14, minus 14. So within the range and within the experimental error. So still, all the samples, they didn't have like a clear hole in the geomembrane to reflect the change in the permeability. Multi-axial test, kind of we found the same thing. Stress at burst did not reflect any physical damage, but elongation at burst reflected the damage. But you can see based on these results, these virgin samples, all those tests that are done with geotextile, they're almost close to the except this one. Again, I should have plotted the results of 3 tests that we did. But it shows that the geotextile is really protecting the geomembrane when we use the gravel. So when you have a sand in it, really doesn't matter. There's not much difference. But when you have gravels without geotextile, you can see significant lowering of elongation at burst. That basically shows that there is a physical damage. So wide strip tensile test, same as field test. There was no differences observed in yield stress or yield strain, but ultimate stress and ultimate strain, they reflected the physical damage. But it's clearly, you can see that when you don't have a geotextile cushion, right, it's failing at lower stress, but when you have a geotextile cushion, it's as good as the virgin sample. Same thing in terms of ultimate strain. So you see that without the geotextile, okay, so these are the results. With the geotextile, you got really, really, really good results here. So very good. So now, what do we make sense out of this one? So what is our recommendation? So just plotted particle size D50 and change in elongation at burst that reflected whatever parameters that reflected the physical damage. I used it here on y-axis. You can see that without geotextile, when I have a coarser particles, there could be more damage, right? Whereas if you have a geotextile, you don't see that much damage. So 0 means, that's like a same as a virgin sample. There are some, differences here. Not sure what that one is, but if you look at this from, other tests, change in ultimate stress, um, you know, uh, you can see with geotextile, it's very close to 0. I mean, there's small difference, but not that much. But when you don't have a geotextile, there could be more, reduction in the stress, and also that reduction in stress, increases with the particle size. So the conclusion out of this one, and you can see the same thing on this one also, that geotextile really protects the geomembrane, irrespective of the size of your granular material. But on the other hand, if I don't want to use the geotextile, the smaller the size, better it is, but increasing size will increase the damage. So obvious conclusion is, okay, hey, for the types of gravel that we tested, using the light geotextile is good enough to protect it, right? So that's the conclusion that we found out here. So in all these cases, we didn't want to increase the size of the granular layer, because remember, it's a 1 foot thickness, because we cannot have a leachate head more than 1 foot. So that's kind of kept constant. And we are looking at these different types of granular soils. And so one point that we particle size, as long as it's less than 30 millimeters, you should not have any issue. But the sphericity is one of the big concerns. And in our tests, we could not capture the wide variation in the sphericity. That could be one thing, could be explored in the future, but that was the conclusion out of those testing. The interesting part about tire shreds, right? So can we use the tire shreds as a drainage layer and not cause the damage to the geomembrane? That's like a big question, right? So we did the same kind of a testing like we did for the granular soils. So we went to the field, we did these different test plots. And obviously you need a heavy geotextile. We know right off of in the beginning, but we used like 8 ounce per square yard is the same as what we used in the soils cases, but we used double the thickness. We used 16 ounce per square yard, and we tested like these uh, uh, tire chips, two types, secondary and primary, and we wanted to have a different thickness, right? 12 inches is the minimum that you need, right? But because it's going to compress, it could compress 50%. But there's no rule that you have to have a minimum 1 foot. But as long as if you have a high hydraulic conductivity and if you can show that leachate head is never going to exceed 1 foot, that's fine too. So basically, we use the 18 inches thickness for secondary layer, and we even tested 36 inches also, and we tested 24 inches. So we varied the thickness of the tire chips. And then here, we use the two types of similar to what we did in the field test in the testing with the soils. But we use the two different types of construction equipment: D6 dozer and the Michigan 275 loaders. So they exert different amounts of pressures, on the samples. We looked at, again, in all these cases, the geotextile is non-woven needle punched polypropylene type, which is commonly used. And tire shreds, as I said, like we didn't take out the steel, so the regular tires, and shred them. And please note that the primary shred had less exposed steel. However, that is whatever the exposed steel is heavier in gauge, whereas the secondary shred has more exposed steel, but is more flexible. If it touches the geomembrane, it probably bends. But if you have a steel from the primary shred touches the geomembrane, there's a chances that it could penetrate into it. So these are the applied loading. The dozer has a 56 kPa pressure, and this Michigan model has 120 kPa pressure. So that's how much is the applied pressure is. Again, these are the test pads that we did exactly like the soils. This is the typical test pad. Again, compacted clay, geomembrane, and geotextile cushion, and then simulating the exactly same construction scenario, and pushing placing the material and pushing it, and we simulated back and forth traffic, turning, braking, and all those things. Again, it's amazing to have regulating agencies interested in these things and making decisions, right? This is like a collaborative work, as I mentioned. Having these guys come and see it, really makes it easy to make decisions. When it comes to, for all these landfill cases, whatever you want to do it, you have to get the permit from the regulating agencies. So they have to approve anything that you want to do it. So having them educated and having them on board is very essential in all these projects. So we did all the testing, and then we took out the samples, right? And then we did the visual observations. And here, visual observations are, you can see, in many cases, we were able to see in one case, a puncture, deep gouge. In here is again, indentation, crease, and needle-sized gouge. So we could see a lot of damage. Here I'm showing you that we found, these are all the cases. AB, basically two samples from that same test pad. If you see it, there were holes found in this one. This is the worst case, I think, if you can imagine. Test pad 5, had a hole in it. That's really bad, right? And then these are the next worst cases where we had distinct deep scratches or gouges. That's really bad. And distinct scratches is also bad. If you look at all these cases, this test pad 1 is good. You had a detectable scratches, but no distinct scratches, no deep scratches or no holes. So that would be the first good case. The other one good case is this test pad number 3, right? So 1 and 3 are good cases to look at. And the other cases, through visual observations, you can say that they are not good, right? So you don't have to do any fancy testing on that one. So here is the first one. What is the first one? You have to use the secondary tire chips. 16-ounce geotextile, and tire chip layer thickness is 18-inch, and using the lighter construction equipment. So if you use that one, you don't see much visual damage. And test pad 3 that looked good visually is also secondary tire chips, 16-inch 16-ounce geotextile, and here is the thickness is 36-inch, double the thickness, and it worked well with heavy construction equipment. So if I'm using the heavy construction equipment, I need to increase the thickness. I can keep the same things here, but if I'm using the lighter construction equipment, I can have a smaller thickness. So that's kind of very interesting results that you can find here. And the ultimate stress results here shown for all the different samples. Obviously, you cut the samples and test them. This wide strip tensile test, wide strip tensile test. Here is the multi-axial test. And based on all these things that we did, turbines was fine, except the test pad 5, which had a hole in it. Obviously, you cannot, if you do any test on that, that's going to fail. And we did multi-axial wide strip water vapor transmission tests on test pad 1, which is considered as the best option out of all these things. So the best option is 18-inch thick secondary shred tire chips with 16-ounce geotextile constructed with a lighter equipment. So then what we did is we took that best condition that we found in the field testing, and we did the long-term testing on that particular condition. So, same way that we did the soils, we did the same thing here. And we did 2 tests. You can look at here. Here is the results for the virgin samples. We did the test 1 and test 2. So here the results, test 1 and test 2 are same, but the ultimate strain in one case, ultimate stress and ultimate strain here, in the test 1 is slightly different than test 2. So this seems like, even though we try to replicate the test, this is important because, we didn't have any control on the tire sheds that were placed at the interface of geomembrane and geotextile cushion, and on the top of it, the tire shed. So, it depends upon randomness of tire sheds that you will have at the interface. That could be some that could be causing some difference in the results, but otherwise, the results are pretty reproducible. So so that's what conclusion out of that one is. If you want to use the tire sheds, you cannot use the primary shed. Remember, primary shed would have been nice to use it because you shed only once, it's economical, but those don't work in terms of the geomembrane protection. So you have to use the secondary shed, but you have to use the thicker geotextile cushion compared to the soils, almost double the size. And you try to use the lighter equipment, construction equipment to use. And we compressed the tires in this lab simulation test, and it worked fine. But as I said, just the randomness of tires at the interface. Some people suggest that you need to put another layer, maybe another layer of the soil, and then put tire sheds on the top of it to minimize the direct contact with geotextile or geomembrane. But any of those things, you can think about it, in your office. But when you want to do out in the field, it's really challenging to even put a thin layer of it, and the costs associated with those things. So overall, what we found is that for 1.5 millimeter thick HDPE geomembrane liner, you're going to use 0.3 meter thick granular soil anyway. You could use any soil as long as D50 is less than 30 millimeters, porosity greater than 0.8, or like the soils that we tested, and use the 270 grams per meter square. It's like 9 ounces. So you construct with that's our recommendation, and that is proven to be effective in the long-term condition also. So just last slide, I want to just mention that what are the lessons? What are the takeaways for especially attendees who are students? Um, these kind of projects. I wanted to present this one to show that we need to identify a real world problem. And a lot of times the industry knows these problems much more than academicians. So it's very important to work with industry and identify the real problems that they are facing, right? So in this case, the landfill owners, they wanted to use gravel that is available close by as the drainage material, or tire sheds that are available to use as the drainage material. But they always used to use sand, but this is a different material. So there were concerns with damaging the geomembrane, and these concerns were expressed by Ohio environmental protection agencies. So we wanted to see how this gravel could be used without damaging the geomembrane. So that's kind of a problem that is initiated by the industry, and then uh, having this collaboration with industry and government agencies is very critical, because universities can conduct the research in an unbiased manner, right? We universities don't have any interest in representing anybody, right? So we do the research in an unbiased way. So working with the university, industry, and government agencies, you can get really have a detailed research program developed to answer the questions or come up with a solution to the problem. And we need to recognize that we can come up with a fancy solution, but it may not be practical. It may not be economical. So we really should always think about what is practical, what is effective, first of all, right? And it should serve the function, and it should be practical, and it should be economical, right? So not if you're proposing something that is expensive, nobody's going to use it. And I like doing these kind of projects, because graduate students really learn about the real world problems, and go through the process of identifying the solutions, identifying the problems, and at the end trying to come up with a solution. So it's a great training for our graduate students. They may not be working on the same research problem in the future, but it's a great training on analyzing the problem and looking at alternatives, coming up with the solutions. And also this gives us the opportunity to disseminate the results for for wider use through publications or presentations like this one. So here are our publications based on this research. So if you are interested in knowing more details on what I covered, you should be able to find those details in these publications. And with that one, this is my contact information. If we don't get a chance to ask question, or you have questions later on, feel free to contact me. I am on Twitter, I'm on Facebook, I'm on LinkedIn. So my email address is here, Krishna R. Reddy. So the middle initial is the one that distinguishes me from other Krishna Reddys. And these are the lab websites you can see for more information on our research. So I want to end my presentation and stop sharing here, and then I'll be happy to take any questions that you have. So I am the presenter, I am the moderator today, so I'm kind of looking at things a little bit different today. So let me just 1 second.